So here's a quick overview of my Redstone CPU so far. It's kind of a mess. We got some fancy registers up top with little lamps so you can actually see the data that's in them. We got my instant carry ALU down here, except people are telling me that it's not actually instant because there are a couple repeaters in the carry line. But I had to do that because it's pretty long. I could have done it shorter with like a under-over design instead of AB, but I had already built this and put work into it, so I wasn't going to change it yet. Here's some RAM. This is 8-bit RAM, 8-bit address, 8-bit data. You got the input right here. You got the control lines, read and write. Got that's address input. This is data input, and here is data output. This tells you like if there's data coming out of the RAM, so that I can have like a variable time for RAM read. Maybe this is all experimental. There's a lot of stuff that isn't built yet. This is the instruction Sub Op Decoder. So I'll explain how that works in a second. So you have the instruction, a 16-bit instruction set architecture with a 5-bit opcode. And the opcode comes in, and let's just like throw some levers on there so that you can kind of see some of the stuff that it can do, or that it does. So like, I'll turn this on and you see we have the opcode gets decoded into a set of sub-ops, which are 5 bits each, and those go into a multiplexer. So you choose your op via these data lines here, via the opcode, and it turns into 5 sub-ops. And I'll just flick through those for a second. You can see it changes because each operation is different. That's a pretty long one. So then these come up through here, get separated out into different layers and multiplexed through. And I can show you a little bit what that looks like. So it uses a clock. Right now it's set to 30 ticks, but we'll see if that's long enough. So that was the reset button, which currently appears to be having some issues. It's supposed to reset to the first one, not the second one. It was working before, but I messed with it and something's not working. But let's just start the clock. I have some of the data control lines connected, so this is probably going to mess with whatever I have stored over there, but for demonstration purposes, you can see that it steps through each of the sub-opcodes, and those get decoded in here into the data control lines. Each time it skips to the next one, it sends a pulse out, so you can actually see those blinking over here. You can't really see it because a lot of the lights are blocked, but over here you can actually see it changing between the different control lines. We got things like flash, ALU bypass, increment, program counter, set if, jump and wait, output, RAM read, reset control states, input, RAM write, update C, register C and flags, lock RAM address, all different things that it can do, or that it needs to be able to do. I had a realization that I should actually have a few of these codes assigned to actually do more than one of these control lines at once, because I have things like load RAM pointer are taking like 8 clock steps right now. That's just a lot. That's really slow for one instruction. Down here, so moving on. Down here we have our register address decoders. Each set of 3 bits is a register address, and those come out the back here. You got register 1 read, register 1 write, register 3, and register 2 read. I don't have write for the other 2 because in my instruction set architecture, only the first register address is actually going to be able to write a value. What else? So it's quite a mess. It's real spaghetti coming out of the control unit here. I mean, everything looks really neat and in line over here, but then once it gets decoded, all the actual control lines are connected to random places, different places, so it's really hard to make it look neat. So like up here, we just have some control lines coming out of the Sub Op Decoder. These lines right here are coming from the register addresses and actually, activating the registers. A, B, and C are built into the ALU, but D, E, F, and G are individually addressable at the top for read and write. Here's the ALU, and you can see the ALU control lines coming in here. So you actually control ALU by it's really simple. In my instruction set architecture, you have a 5-bit opcode, but only 4 of the bits are actually really used to define an instruction. The first bit is actually just switches between ALU or instruction. So it should, when ALU is turned on, oh, see, right, I made a mistake because that needs to actually carry along there. So I'll turn that on, and now the ALU is sending a value into, sending some control signals into the actual ALU itself, and I can change this to a different one. It's got a number of controls. So we got invert A and B, or flood carry, carry in if the overflow flag is on, barrel, left shift, and right shift. That allows you to do lots of different things. And then below, so you got the data control lines, register control lines, ALU control lines, and then down here is the if module. And this allows you to do things like, I don't know, do this if this value is equal to or greater than or less than, or any of the, so the different ifs that you can use. You can check if the negative flag is on, or 0, or overflow, or carry / underflow. But you can also do 3 separate sort of math, I guess you would call them, if statements. So you can do A is greater than B, or A is less than B, or A is equal to B. And those actually work by sending a control line up here, which does subtract in the ALU, and subtracts the numbers and then checks for they either carry or underflow or neither. And the cool thing about this is you can also, I use the last bit in the instruction for the if instruction to use as a checking for on or off. So you can check if a value is true or false. So that gives you actually all the inverse of these math. So if you want to do like A is not less than B, like A is either greater than B or equal to B, you can do that via this. What else? Here's just a closer look at the opcode encoder. So some steps for let's go load RAM. load RAM. That is a really long one. It's got 8 steps. Like I explained earlier, I'm going to condense that, but we got lock RAM address, block immediate, read RAM and wait, reg1 write, and such. Actually, load RAM pointer is longer, but you get the idea. So a lot of stuff going on here. This RAM is pretty big, which also means it's kind of slow. I mean, if you're addressing like low address points down here, it's relatively fast. But if you're addressing a value that's stored like way up there, first the address has to go all the way up, and then the value has to come all the way down and come out before you actually get a value that you can use in the CPU. So that slows down the registers, or I mean the control steps. Now look at this, it's doing something funky. I'm gonna have to fix that. There's not supposed to be 2 of these active at once. Anyways, obviously I have some work to do. It's not done by any means. I mean, even the instruction set here, only the opcode for the instruction is hooked up. All the rest are just dangling wires here. So lots to do, but I'm learning as I go, and this video is 11 minutes and 30 seconds long, so I'm going to end it now.